Um, right. So, so what was I going to say? Oh, so for my benefit, when you send me your homework, could you put your name somewhere in the title of it and the title of the file you send me? And if possible, remove any spaces from the title of the file. It just makes those of us who are still preferring command line to move files easier if there are no spaces or funny characters in the titles of the files. Um, it do just make things a little bit easier for me. I have already received the homework from the vast majority of you. And if you're sending it to me, sort of right at the last minute, I haven't looked at my email in the last few minutes yet. Uh, and I will do my best to acknowledge that I received the homework from all of you. And if I don't acknowledge that I received it, you never got an email back from me. Assume that the email got lost somehow and resend. What was I going to say here? Um, I don't know. The grading of it. So the homework is graded on, did you turn it in? Did you turn it in and make it look like you tried your best on all the problems? If the answer is you turned it in and made it look like you tried your best on all the problems, you get a full score. If you didn't turn it in, or didn't, or it doesn't look at all like you tried your best, you probably won't get a full score. But there is, um, it is being collected simply to encourage you to have done it and to have done your best. And um, the your best is fine. And if they're all right, spectacular. If they're not all right, during class, we'll get that figured out. And hopefully you'll know what the correct answers are by the end of class. And there is certainly no reason to send me ever any corrected homework or, or anything like that. I think it might be a good idea for you to keep a corrected copy if you didn't get everything perfectly the first time around. But you don't need to show that to me. I'm happy with your first effort, however it was, but before the exams, you're probably going to want to sort of get it all straightened out. Does that make sense? Anybody have any questions? So as promised, I have a randomized list of your names, and I'm going to run through that list and get you guys to do some or part of all or part of a problem when it is your turn. And, you guys are teaching each other the class. So we begin with Shengxi doing problem one.
Okay, I'll just go ahead and share my screen.
I think that'd be perfect. Have I given you rights?
I'm not sure. Let me pull out my stuff first. Okay, I think I should be able to share my screen.
Okay.
No, I think you have to give me permission
There
to
we
do
go.
that.
Try again.
Okay. So I think you should be looking at my screen, which is basically a Google Colab notebook, or a Jupyter notebook, if you will. The first question is, let x be a Bernoulli random variable with probability p that x equals 1 and probability 1 minus p that x equals 0. And we want to find the first, second, and kth moment of the random variable. So the first moment, which is the, I guess the mean of x, is the value of x when it's equal to 1 times the probability that the random variable will take on the value 1 plus the value of x when it's 0 times the probability that x will be 0. And this would just be p. And then for the second moment, or the kth moment, the idea is to take the value. So if you want to get the expected value for the second moment, you will take 1 squared times the probability that x will take on 1 again, plus 0 squared times the probability that x will take on 0. And if you just do the math, it ends up being p. And in general, for the kth moment, the expected value will still be k. Sorry, it will be p for the Bernoulli random variable. And then for the variance of x, so the variance of x is given by the expected value of the square of the difference between x and its expected value. So if you just expand the square inside the expected value, you end up getting x squared minus 2x times expected value of x plus expected value of x squared. And since the expectation is a linear operator, you can just, I guess, yes, it's a linear operator. So you end up getting expected value of x squared minus 2 times expected value of x squared, basically, plus expected value of x squared. And this ends up being expected value of x squared minus the square of the expected value of x. And this would be p minus p squared. And the standard deviation is the square root of the variance. And so that's square root of p minus p squared.
Couldn't have been done any more perfectly, including solving problem 10 or something along the way.
Solving problem 10, yes.
Does anyone have any questions about that? That is exactly perfect in every way.
Okay, thank you.
Taylor, would you like to do problem 2?
Sure. Okay, so I didn't actually type out the problem itself in the homework, but I can kind of summarize what we're going through. So we're considering a normal 6-sided die. Each side is labeled with numbers 1, 2 through 6. And when you throw the die, each side is equally likely to end up on top. So we're letting x be a random variable. That's the value on the top side of the thrown die. And we're looking to find what the mean and variance of x is. Okay. Can everyone see the screen? Good. Okay.
Good to me.
So just by the definition of the expectation of x, we're basically summing over the sample space, the values that x can take, which is 1 through 6, and multiplying the value that it takes by the probability that x takes that certain value. So we're summing from 1 to 6. The probability that x equals 1 through 6 is all the same. It's 1/6. So we can pull that out to the left. And basically, we're left with 1/6. That's the summation from x equals 1 to 6. And we can write that as 7/2. Very similar approach because we can write the variance of x as also as an expectation. So we know that the variance of x is the expectation of x minus mean of x squared. So again, we do our summation from x equals 1 to 6 of the value that x takes minus the mean of x, which is 7/2 squared, times the probability that x takes that certain value. And again, the probability that x takes either 1 through 6 is the same. So it's all 1/6, and we can pull that out to the left again. We're left with 1/6 times the summation from x equals 1 to 6 of x minus 7/2 squared. And I was too lazy to do all the fractions, so I left it as 2.917.
And that's fine. It might be something like 35/12 or something if we put it as a fraction.
Cool.
Something like that. Does anyone have any questions about this? These are all both just straightforward definitions of expectation and variance. Okay. Problem 3, I think, has, oh no, problem 3 does not have so many parts. So yes, it does. So let's go with Christopher for problem 3A. Chris.
All right.
And why don't you set the whole problem up for us, if you could?
Yeah, sounds good. Let me share the screen here. You guys see my screen?
Can.
Great. Okay, so the problem is to let x1 and x2 both be Bernoulli random variables with common mean p. Assume that x1 and x2 are independent of one another. Let s equal x1 plus x2. So I can see here that I did up a bit of a table here. So I've got the values of x1 and x2 on the left, and then the value, I guess I should probably label this S. And then the probability of each of those outcomes. So the first questions was the probability of S equaling 2. Well, we know that the probability of x equaling 1 is 1 minus p. The value of x minus 2 is 1 minus p. And so we get this answer here after multiplying this together.
Absolutely. You'll probably find for a lot of what we do, keeping things as 1 minus p might be might lead to solutions being in a more compact form than multiplying p times 1 minus p or multiplying 1 minus p squared out. You maybe not, but for a lot of purposes, I think it might be useful. You'll find it useful rather than to multiply it up. You'll see as we go on. Just it might simplify some of your algebra.
Sounds good.
But that's that is in no sense a comment on the accuracy of what you've written. It's more a comment on the. I think you'll find the algebra simplifies more often when you leave it in that form.
Cool.
But just a hint. Well done, Young Shan.
I had a question.
Yes. Oh, sorry. Please.
I did not get those probability values for the individual S.
All right.
I didn't know if those were correct or incorrect.
Let's pop them up. Christopher, you should pop them up back on the screen so we can talk about them.
Yeah. Oops. That's the right one. Oh, I don't think I'm sharing the right screen, am I? 1 second.
Or
Sorry, I guess I didn't learn very well from last week. Okay, I want the homework assignment. Share. Okay.
so Christopher, talk through why the value of S is p squared there.
Sorry. So the question is, why is the value?
I mean, S for 0.
Yep.
Is it really p squared or should it be 1 minus p squared? I suppose is the question. Which one?
Oh, yeah.
Which one is p and which is 1 minus p and so forth.
Right. Yeah. Well, I guess I guess you could do it the other. I guess you could make it one.
I hadn't actually noticed. Which way does the problem suggest we should do it?
Yeah, I think it suggests it the other way from what I did. Yeah. So this line here should just be reversed with this, if that makes sense. Yeah.
So the probability of 0 and 0 is 1 minus p times 1 minus p. The problem of 1 and 1 is p times p, and one of them is 0 and one of them is 1 p times 1 minus p and vice versa. I didn't even notice we flipped them. You can.
Yeah.
And was that your concern that they were flipped?
Yeah, I just got worried that I flipped them.
Nope, we did. Sorry, Mitchell.
Sorry.
Didn't even notice. Well done. Thank you. Did anybody else notice something was flipped like that I didn't notice?
I had, I think some of them, I had p squared too, and I was like, wait, hold on. How did I get to that? And I was just tracing back my work.
You're right, we're wrong. Other questions? All right, Yun Xiang with 3B. Is she on yet? Maybe she's, oh yeah. There we- Wow. That's an image.
Sorry, can you all see my screen?
Yeah. I mean, there's a dancer or something on your screen.
Yeah. Huh. right. So for question 3b, we're gonna see what's the probability that s equals 1. There are two ways that s can be 1. The first one is x1 being 0 and x2 being 1. And the second one is
We can only see.
Oh,
Yeah.
really?
Yeah, we're looking at a dancer's arm in a pose.
Oops. Sorry.
We can just see your desktop.
Sorry.
Ah, there we go.
Is it okay? All right. Sorry about that. And then to like for s to be 1, there are two ways. The first one is x1 being 0 and then x2 being 1. And then the second way is x1 being 1 and x2 being 2. So this will be 1 minus p, which is the probability of x1 being 0, and times p, which is a probability that x2 being 1. And these two can be multiplied because they are independent. And then also we're gonna sum p times 1 minus p, which is the second way that s can be 1. So this makes the probability of s to be 1 equals to 2p times 1 minus p.
Beautiful. Does anyone have a question? Carmen, how about part C?
Yeah, let me share my screen. So I actually did it incorrectly because I assumed that I like pulled a p-value out of like probability value out of nowhere, but
Okay.
as we were like going through everything, I kind of like realized my mistake.
Excellent.
So oh, actually maybe not. It would be okay, so
You're right the first time.
oh, okay, cool. Okay, so the probability of s equals 0 would be the probability of the way to get it would be for x1 equal to 0 and x2 equal to 0, which would be p times p, so it would be p squared.
Oh, is this 0 or is this 1? I'm sorry. Are we doing I'm sorry. What is the question asking for?
I think I was.
I thought it was asking for s equal 2, but maybe it's asking for s equals 0.
Yeah, I thought it was s equals 0, so it would be this.
It's asking for s equals 0. Yes, sorry. Yeah, so it'll be 1 minus p squared. Perfect. Yep. Sorry, I can't see my own problems while the screen isn't full. But the probability of 2 is p squared. The probability of 1 is 2 times p times 1 minus p. And the probability of 0 is 1 minus p squared. I got them all. Do we have questions? Does it make sense? That we have two independent Bernoulli random variables, so we can go through all their possible outcomes and multiply their probabilities to get the probability of the joint outcome. Everybody's okay? So Mitchell, you want to do part D?
Sure. I unfortunately do not have as nice a looking stuff to share, but it should work.
Yeah.
Can everyone see my written out file?
Yeah.
My PDF. So I was doing D, that's the mean of S. So the mean of S is just the sum of the probabilities times the value of S. So now that we have each individual probability, you just multiply the probability you have by the value S it has. So we only have 3 states of S, 0, 1, and 2. So you just multiply those together and then simplify this equation. So those are just it written out. Not sure if I simplified it correctly.
You certainly did.
Oh, cool. And that's that.
Does anyone have any questions? That is,
Yeah, I think I got that wrong. I got p squared and I don't know why. I just multiplied the expected values for the two x variables.
do you want to show what you did? and we can take a look at it.
Sure. So yeah.
So that where you have a multiplication, you mean to have a sum. The expectation, so S equals x1 plus x2. So the expectation of x equals the expectation of x1 plus the expectation of x2.
Okay, that's where it went wrong.
Yep. It's that little multiplication sign in between them should be a plus sign. And if,
Okay.
and if you if as Zhang Xi said, expectations are linear operators. So that if you have the expectation of A plus B, it is the expectation of A plus the expectation of B. And
I don't really remember, but does that depend on independence?
it does not.
In a terrible way.
It does not.
Okay.
It is a strong result. The variance depends on independence, or rather, the full result will have a covariance in them. But the expectation is a linear operator, full stop, for any two variables. Other questions?
I had one kind of weird one.
Yeah.
Sorry, I'm eating my breakfast.
No, please, it's early for most of us. Anyway.
When these values are 0 and those terms drop out, it just feels weird to me to eliminate from the equation for the mean a whole value just because it had a value of 0. I don't understand that.
Well, so the way to think about it is the expectation is sort of it's kind of like a weighted sum. It is the sum of all of your values weighted by their probability. So when you add up a whole bunch of numbers, anytime you add a 0, doesn't change it. So you can add any number of zeros and that sum will remain the same, no matter how you've even weighted it, unless you've weighted it, unless you got a 0 divided by 0 or something. But that's probably the best we're going to do for intuition. The other intuition is you might imagine that all random variables have mean 0. And every time they take on a value 0, it doesn't move their mean away from the default guess that their mean was 0. And that'll be true for a lot of continuous random variables that we look at, like normal distribution.
Okay.
Other questions? All right, I think we are on problem 1 with Michelle.
Okay. Can you see my screen?
We can.
All right, so E, what is the variance of S? So the variance of S is defined down here as the sum of the expectation of x squared minus the expectation of s squared.
Almost problem 10 to know that, probably, but great.
Yeah, so this is proved in problem 10, but also I just pulled it out of the book here. So before getting down to the variance, I just figured out what these two terms were. So the expectation of s squared is just 2p squared, which is 4p squared, based on what we found in part D. And then the expectation of s squared is the sum of all of the probabilities of s times each value of s squared, which I went through algebraically here and came out with 2p times 1 plus p. So then just filling those into our equation here, expanding it, and then finally getting 2p times 1 minus p.
Well done. Does anyone have any questions or comments? Any alternative versions they want to share?
I did it just a little bit different, but basically with the equivalent formula. But yeah. Huh?
From the definition originally?
Yeah, so if you can plug in the value of the mean, and then without
Do you want to show it? Go ahead.
oh sure, yeah. 1 second. Okay, let me scroll up just a little bit. I'm sorry. So here is where I was looking at it, where just similar to Michelle, but just a slightly different, another definition for the variances. You can take the expected, I basically did variance of x1 and variance x2, and then I had the expectation, this is also equal to the expectation of x1 minus the mean squared plus the expectation of x2 minus the mean squared, which when you start plugging in values, you'll get p, so the probability times x minus the mean, same thing here, you add it together, reduce it down. Actually, I think that's right. Maybe I didn't do that quite right. I think.
So the first sentence is not quite perfect in the sense of the variance of S is the variance of x1 plus the variance of x2 plus twice the covariance of x1 and x2.
Oh, okay.
You then use,
I did this.
You then use the fact that x1 and x2 were independent to infer that the covariance was 0 and didn't bother to calculate the covariance because you knew it was 0. And
okay.
you didn't bother to write it because you just assumed it all.
Yeah.
But from that moment onward, we now have the variance of a sum. And you have variance of x1, which you showed in the previous problem was p times 1 minus p. And the variance of x2, which you showed in the previous problem, is p times 1 minus p. And then you added the two together beautifully.
You can explain it better than I can.
Yeah. It's very slickly done, and that is probably the easiest way to do that problem. But you have to use the fact that the covariance is 0 to
right.
make that quite work.
I'm actually just going to make a note about, because I want to make sure I can show that covariance anyway, just later for my own notes, but I'll stop sharing.
Does everyone understand that? And that should complete problem 3. And let's go with Jim, for problem 4A.
Sure. Let me get it going. All right, you guys see the screen? Assuming you're seeing my work.
Very pretty.
So I did this table. The question was, let x1 and x2 both be independent, identically distributed Bernoulli random variables with mean p. X3 is another Bernoulli with mean f. And we have this new variable s, which is according to these kind of if statements. And so I tabled that out. I figured there's 8 different arrangements of x1, 2, and 3 kind of laid out here. And then when you go through this logic, you can see that s, depending on the 3 of them, is equal to each of these values, given the different conditions based on x3. And then you can calculate the probability for each by just taking, what we know about the means of the different Bernoulli variables. And so for A, the question was just, what is the probability of s equals 2? So we just look here and we see here's s equals 2, as well as here, and I think these as well. And maybe actually I've missed one in my answer.
So backing up a second, because these things are coming in kind of crazy order. There should be, what you said, 8 of them.
What was that? Sorry.
Do you see 0, 1, 1 anywhere?
0, 1, 1. I may have missed one. I was looking for a way to find all the answers, all the combinations. I don't know enough about the, combinations, permutations to figure that out automatically.
The easiest thing to do is probably to start with say x1, x2, and x3 all of 0, and then make x3 equal to 1, and then make x2 equal to 1 and x3 back to 0, and then make x3 equal to 1, and then make x1 equal to 1 and x2 and 3 equal to 0. It's like you're counting in binary. It's like the number starts at 0, then it becomes 1, and then it becomes 2, then it becomes 3, and then it becomes 4, and then it becomes 5, 6. That's probably the easiest way to make sure you end up with all of the combinations in there.
Yeah, so I started with just all ones and all zeros, and then I kind of did this diagonal, and then I tried to think of the doubles.
I think, oh, you have double ones twice in there, or triple ones twice in there. And
Yeah, I do, don't I? That's what
Yep.
it is. Yes.
They're missing 0, 1, 1. Okay.
Aha, that's the missing one. Okay.
Yep.
0, 1, 1.
Anyway, this is absolutely the correct way to approach the problem. And if we've gotten them all, if we've gotten all 8 enumerated correctly, and yeah, so you had one extra s equals 2.
Yeah, so this doesn't belong. This bottom one.
And
what should that be? That should be 0, 1, 1. So that's x3 equals 1. So it's 0.
That's it.
Right? So
Yep.
s equals 0.
That should be an s equals 0 there.
So it's not important for s equals 2 in part A.
It is, because you have an extra thing presumably in there. You have you have one extra 2.
Yes, because so
or maybe you didn't
for
put
some
it-
reason when I actually went and did the problem, I didn't count that last row.
Hey, you got it right either way. Yeah, very good.
So you just add them up. You add up the probabilities for each of the 2s, which is here. Oh, and for me, I just said Q is 1 minus P, just to make it simpler. I should have said that somewhere, but I didn't.
So that looks like P squared. Yes. Does anyone have any questions about this? This makes sense to everybody?
Yeah, I realize that for me, for 4, I think I kind of approached the ABCD a little bit incorrectly. And I think I just need to go back to the fundamental definition where we're adding the terms, and why are we adding the probabilities again and not multiplying them?
We're multiplying probabilities.
Okay.
Often adding, so because the problem asks us, to say s equals x1 plus x2, that outcome s is the sum. But when x1 and x2 are independent of one another, the probability is their product.
Oh, okay. So we are multiplying them.
So to go through this Jim's first line, he has x1 equal 1, which he has as occurring with probability p. He has x2 is equal to 1, which he has occurring with probability p, and he has multiplied them together to get a p squared. And then he's gotten x3 equals 1, which he has occurring with probability f, and he's multiplied all 3 of them together to get fp squared. For the next line of 0, 0, 0, 0, he has the probability x1 is 0 is q, the probability, which is 1 minus p in his notation. The probability that x2 is 0, he has a 1 minus p again, and the probability x3 is 0 is 1 minus f. He has multiplied them all together. In the s terms, he just follows the crazy logic of the problem, where he says, when x1 and x2 are both 1 and x3 is 1, add x1, no, take 2 times x1. And that's what he did. He multiplied 2 times x1, and got the number 2. And then he followed the crazy logic of the problem for the next one. When x3 is 0, add them together. x1 plus x2 is 0. When x1 is 1, x2 is, when x1 is 1, x2 is 0, and x3 is 0, x3 is 0, So add them together.
Okay. So basically it's just plugging in the because you can add like the x1 plus x2 is also equal to the probability of x1 plus probability of x2. Is that?
I would think of the probability of these events is the product of their individual probabilities because they're independent.
Right. Okay.
The value of S is just some crazy set of rules.
Yeah. Yeah. That's what I'm trying to understand is like the rule, because
S is just an astonishingly odd random variable that was constructed from these three random variables in a weird, non-linear, kind of odd, unexpected way. This problem is human inbreeding, but that's a different subject entirely. But next week, you will see this is called generalized Hardy-Weinberg. And if you read the book, you will see it derived as a function of inbreeding. But it is in fact just a complicated series of Bernoulli random variables. Other questions? We ready to move to, so that was 4A. Julie, you want to do 4B?
Sure.
Yeah, so 4B is asking for probability of S equals 1, and there are two scenarios for S to be equal to 1. One is that when x3 is 0, x1 is 1, and x2 is 0. The other is x3 is 0, x1 is 1, and x2 equals 1. So since these variables are independent, you just multiply the probabilities of these independent events, and you add them up to get 2 times y minus f times p times y minus p.
Beautiful. Absolutely.
Thank you.
Any questions? All right, Marissa, do you want to do 4C?
Yeah, let me try to share my screen. I can't get the right page to display.
Can you get the right page to display? Once. So when you go to sharing, do you have it open on your desktop somewhere?
Yeah, so the issue is I'm using this program and it's just not working correctly for me right now.
Okay. Okay, well, try to get that.
Okay.
Oh, you got it?
I think I got it.
Oh.
I mean, I got the answer wrong, so it doesn't matter,
okay. That's okay. Ah, got it. Very good.
yeah, so, yeah.
Problems 8 and up. Can you sort of?
What?
I think
this is page 4. I just did it in an order I preferred.
Oh, I see. I'm sorry. I gotcha. Okay.
Yeah, so see, I thought it was based on that graph, this part, but then looking at my peers' work, then I thought it was this, but it's still wrong, so I don't really know.
Why do you think well it's close, that last bit. So it looks very close, that last bit. So it turns out there are 3 here. I'll share my screen if I can. Oops. This will stop others sharing their screens. Okay, that's fine. I'm going to share mine. And so can you guys see my version of this? Can anyone see it?
Yeah.
Yep. So I had, for s equals 0, I had 3 possibilities. x1, x2, and x3 were 0. x1 was 0, x2 was 1, and x3 was 1. And missed one. And x1, x2, that one, this one, and this one. So x1 is 0, 1 minus p. x2 is 0, 1 minus p. x3 is 0, 1 minus f. x1 is 0, that's a p. I mean, that's a 1 minus p. x2 is 1, that's a p. x3 is 1, that's an f. And oh, here's the other one. x1 is 1 minus p. x2 is 0, that's a 1 minus p. x3 is 1, that's an f. So you add up those terms, 1 minus f times 1 minus p squared, f1 minus p and f1 minus p, you add those all together, and you get 1 minus p squared plus fp1 minus p. There's probably a lot of ways to write that final answer. But for all of the, well, no, I actually didn't do it this week, but there's probably a few different forms of that answer. Questions?
Can I make maybe like a question / comment that I think, because I got the same thing and I think I kind of realized what I did wrong.
So, something?
Yeah, I could just share.
Oops, I got to stop.
I guess I could. Yeah, I think so.
I'm the boss, so to speak. Oops, have I done something really wrong? There we go. Sorry.
Okay, there we go. I think the problem for me was that, oops, go back here. So when you're talking about like the first outcome where x3 is 1 and s becomes 2x1,
yeah.
I think I noticed this on a couple other people's work too, and I made the same problem, which is just that for like the first outcome, when say you have x3 being 1, it seems like the probability should be irrelevant of x2 because x2 doesn't play into s at all. So that's where I got this answer, which I saw, I think someone else had it as well. And I guess you have to multiply x2 by those other things that x1 could be as well in order to get the total probability.
That's it, exactly. The thing you wrote down, like if you are correct. You don't need, well, you need to sum over all possible values of that missing irrelevant x2, so to speak. That what you put down is something like a marginal probability with and you need sort of over all possible values of x2 in there.
Okay, so then if you just wanted to patch up the C, I guess here, you would just have to put in that what's the probability of x2 being 1 or 0 as well, I guess. And then I think that would be all, I think.
Yeah.
Cool.
You're gonna have 2 cases there. One of them where it's the probability of 1 and the other where it's the probability of 0.
Right.
Although, wait, that's correct.
I guess
the solution is correct then.
This is correct?
That's totally correct. You have summed over both. If you haven't popped the probability of x2 in there anywhere, that's just correct as written.
Oh.
That is equal to
okay.
f plus 1 minus fq squared. That's totally correct.
Oh, okay.
Yeah.
So
sorry. One probability of x2 in there, you have to have all of them.
Oh, okay, I see. Okay, so we don't necessarily need to add this stuff. Okay, gotcha.
You have already integrated over all the possibilities of x2 there in your head. If that makes any sense.
I might have to think about it a bit more.
All right.
I guess, yeah, because we did, I checked to see if it probably summed to 1 and they did, so which made me convinced that it was probably right, but
Yep, nope, totally correct.
yeah.
That's just,
Okay.
you have it written in a slightly different form than some of the others.
Yeah, I'll stop sharing my screen. There we go.
Anyone else want to talk? All right, are we on to 1D with Brooke?
All right.
I mean 1D, 4D, sorry.
4D, yeah. It's okay, I was following along at home.
Yeah.
All right, 1 second. Okie dokie. So I think that based on some, we're gonna see if I got this, because I think I was doing things a little bit funky in my A, B, and C, but this might still line up. So the mean of S is going to be the expectation of S, and that is dependent on what the value of X3 is, which can take 0 or 1. So I am going to try to annotate since I know I'm kind of in a funky place, but we're looking here. That was worthless. Right here. What that is, and I apologize for my notation here. I know it's not sort of conventional, but it's basically the expectation of S being the sum of the probability times the value of S and the sum of the variations of the values at 1.
Okay.
And I think I'm already on the wrong track.
No, you're very much on the right track, but I want to formalize this a little bit. The expectation of S. Can I draw on your screen?
I think you can.
Where do you find that silly little tool that you have there?
So you can go to, there's a bar at the top. So when you're looking at your Zoom, there should be participants, new, share, pause, annotate. And you should be able to annotate. I think you can.
I can't probably because I am not the owner of the screen right now. I think maybe I
think you still can because
Yeah,
I
you
just
should be able to.
Oh, what do you think I should be able to?
Do you see like a green bar at the top with like view options?
Yes.
In that options, there's an annotate feature up there.
Thank you, guys. So what you have here, oh my God, this is so slow, is the expectation of S is equal to the expectation of, this is too childish, the expectation of S given X3. So the expectation of something is equal to what was referred to earlier as the iterated expectation of the expectation of that thing given something else. So the expectation of X, there is a formal expectation on the outside here. I wish I could, am I drawing again?
Oh, I think you might be, but I think. So basically there's a whole extra
around this.
expectation.
There's an expectation around the S3, the S given X3 term, and there's an expectation around the S given X3 term here.
I think I entirely missed that concept.
Yeah. So what you have is, I can find the expectation of S by taking the probability that X3 equals 0 and multiplying it by the expectation of S given S3 equals 0. And then add to that the probability X3, that should be the probability X3 equals 1, but that's just a typo, times the expectation of S given X3 equals 1.
Yeah.
So showing that here, can you see sort of how I've written this out? that the can you guys see my screen?
No, so I can't see your screen or if you're writing on mine. Oh,
Can you see it now? Can you see?
Yes.
Yeah. So we should have the expectation of S is equal to the expectation of the expectation of S given X3, which is the probability X3 equals 0 times the expectation of S given X3 is 1, probability times the expectation. That probability is 1 minus F. And when X3 was 0, I can't remember what the rule was, but you multiply a Bernoulli by 2. And when F was equal to 1, you add 2 Bernoullis together, or vice versa. But either way, whether you take one Bernoulli and multiply it by 2 or add 2 Bernoullis together, you get an expectation of 2p. And that's that. So the expectation is 2p. Does that make sense, Brooke?
I think so. I mean, it might just be that I need to work it out again. I think I'm trying to understand just the notation itself of
conditional expectations are odd things and are probably not something you've played with very much.
It's the wrapping of the extra expectation that I think I'm having the most trouble with, because I get this, or I think if I was on the right track, I think when I was writing out the expectations, I was applying the probabilities from the rules. So I had created a table similar to my classmates. And so I was starting to apply those in and fill in the values, but then I ended up with 1 minus F times 1 minus P squared. And I think that's where it got lost, because maybe I needed to apply another expectation on top of that.
So if you put your answer up, we can actually show you exactly where it went slightly wrong.
Okay, yeah. Okay.
So because there is supposed to be an expectation around that S given X3, that should be the answer to that X given X3. That number is just, it's going to be 2p. The expectation of S given X3 is 0, or the expectation of S given X3 is 1, is 2p either way.
Okay, hold on, let me think. Okay, so the expectation is.
So the probability.
Oh, okay, you know what I am doing? It's my brain not wrapping around the idea. So what I want to be doing in my brain is taking all of the probabilities and just putting them together without actually filling in their multiplier, which would be 0 or 1. I think that's why I'm having the funky time.
Okay.
So if I were to multiply by 0 and I were to multiply by 1, then it would reduce down and it would become 2p.
Okay. Right? I'm not quite sure exactly what you have in mind, but
okay. I'm sorry to interrupt. I'll let you.
No. You're just gonna. I just wasn't quite follow. You could show me, and we can talk about it later. But the idea of an expectation is it can be done very, very formally. It is always the sum of every possible outcome times the probability of that outcome. So when you add a conditioning in there, what it does is it limits the kind of outcomes that are possible. So when you add a conditioning on X3, you're talking about so in a very formal sense, the expectation of X given X3 is the probability of one value of X3 times the expectation of X given that value of X3 plus sort of summed over all potential X3s. It's not practice. We'll practice. This will become more familiar as we practice more and more.
Excuse me, can I say something about this problem?
Sure.
I had a different way to do it. If I can share my screen.
Yes, actually, what did you do a transformation of variable?
Yes, I did a transformation of variables. Yeah, so
much easier way of doing this.
So, yeah, so there's a different I guess a different way of looking at it. So originally we had if x3 is equal to 0, then s is equal to x1. And if x3 was equal to 1, then s is equal to x1 plus x2. Okay, so instead of having to worry about conditioning on x3, we can rewrite s in terms of x1, x2, and x3. So rewriting. So okay, so I'll let everyone take a look for a second and try to understand. So the idea is that if x3 is equal to 1, then this term, the 1 minus x3 times x2 term, this would be 0. So we end up with s equals 2x1. And if x3 is equal to 0, then we end up with x1 plus x2. So I guess, so it's important to understand this step because this is the most critical step in doing this problem in this fashion. So once we once we can see why we can rewrite s in terms of all three of these variables, and also we know that all of them are independent. Okay, actually, the independence part is only useful when we have to do the variance.
Yeah.
Okay, so now if we want to just compute the expectation of s, this is just the expectation of x1 plus x3, x1 plus 1 minus x3, x2. And because expectation is a linear operator, this is the same as expectation of x1 plus expectation of x3 times expectation of x1 plus expectation of 1 minus x3, which is the same as 1 minus expectation of 3 times expectation of x2. And I think expectation of x1 is p, if I'm not wrong, p plus f times p plus 1 minus f times p. And if you simplify this, this is 2p.
Mm-hmm.
Okay.
So the reason that you can, because this is reminding me of something from way a long time ago. That first combination of your where you're defining s in terms of all three variables. I think I'm just trying to see
The
how
answer,
you could.
Okay.
the answer is he got that by literally just seeing it. So plug in x3 is 0 and see what you get.
Right. So, I mean, x3 is 0. Well, I mean, I understand that. So like if I were to plug in the values, I could get, I know how I would combine it down, but what I'm wondering is like, how would, like, am I just like, how do I go backwards in time? So like, I know that I have 2x1 and I have x plus x1 plus x2, but if I wanted to rewrite them in terms of s, I think, I'm sorry if I'm taking up time. I just.
No, I don't think there's a good way of getting this other than to see that as the solution, other than to see that will give you the right answer.
Wait, aren't those flipped? Sorry, wait, if it's 0, then you'll have x2 in there.
Oh, did I flip this?
Oh, you might have.
I might have. Okay.
Yeah.
So let me correct this. So okay, since expectation of x2 and x1 are the same, I guess the final answer is due. This
Oh wait. Okay, hold on. Wait.
I thought this was the way it was. I thought if it was 0, wait a minute, which way? If x3 is 1, I multiply them by 2.
Okay.
And if x3, okay, yeah, it is backwards.
Okay, there we go. Thanks for catching that.
So what is this called again when you do this?
This is not
I
even
guess-
quite a transformation of variables. It's more like just a rewriting of the formula. Might be called an expansion. But, well, you do this the same way, right, Taylor? I think I saw you do this the same way. Yeah. This is somewhat helpful on this problem, but there will be a transformation, a sort of proper transformation of variables on the next problem that turns a mountain of algebra into a molehill of expectation and variances. That'll be a lot more useful. But this is still easier than cranking through all the sums of the probabilities, I think. This is just it is just a fact that S, as I defined it, is equal to that formula. And I don't think there is a good way of knowing that without intuiting it.
Maybe is there, well, maybe I can ask you about some resources of just reviewing that kind of,
Yeah. Other questions?
I might have like a simpler way of deriving this transformation, just kind of thinking about it.
Oh, go ahead then.
Should I stop sharing?
Yeah, just
Okay.
to think it's a little bit easier to kind of understand it this way. Okay, can you see my mouse or no?
Yep.
Okay, cool. So the way I always think about it is kind of like in terms of indicator variables. So S takes 2x1 if x3 is equal to 1. So I put that x3 there, and it takes the value x1 plus x2 if x3 is equal to 0. So I put 1 minus x3 there. So when x3 is 1, you get 2x1. This term is 0, so it drops out. When x3 is 0, this term drops out, and this term equals 1.
Yep.
And you get x1 plus x2. So that's kind of how I came about with the transformation.
It's a nice way of seeing it. Does anyone else want to comment? Okay. Did you make it on, Kevin? Are you here for the next set? For the next?
I am.
Okay. I think we're on to section E of problem 4.
Okay. Let's see. Desktop 3. All right, so mine's written out, and I did a lot of like. So it looks pretty bad. Let's see if I can like zoom in here. Maybe I can't. I don't know. Let's see. Oh, there we go. All right. So the way I pursued this problem is like basically using this principle here, which is the variance of S is equal to the expectation of S squared minus the expectation of, or the expectation of S squared minus the expectation of S squared. We actually already know the expectation of S from the previous problem, which I wrote out here. So I just squared that and kept it kind of like by itself. But I added it on to this part of it, which is basically taking the expectation of S and taking S and squaring everything. So I squared 2 squared, and then I have like this is referring to my answer in A and my answer in B.
Perfect.
And squaring the value 1 here. So I basically worked all that out. It's ugly. I don't know how I got there. I mean, I do, but like it was just ugly. And I basically boiled it down to this here, which is 2pq plus or times 1 plus f. Because I did this little identity here. So, but this is the really important part here is kind of like this idea, and then taking my previous answers and plugging them in here.
That's it exactly. A straight definition.
Yep.
And yes, 2pq 1 plus f is probably the neatest form you're going to get that solution in.
Yep. Yeah, it's definitely hard to keep track of all the things. When I was writing this out, I remember just be like, where's my f's and q's and p's and so.
The algebra probably gets cleanest if you start out separating f and non-f terms and sort of keeping them separately. But there's no super clean way of doing this. The transformation of variables makes the variance calculation a little bit easier, but because so many things are independent there. That was the main reason to have done it.
I guess the important part too is also that there's a 0 here that I'm not representing because that's part of like
0 squared is 0.
Yep, exactly.
Does anybody have any questions? Would one of you like to show how slick the variance was when you did the transformation? You want to show that, Taylor or Shang-Chi?
I didn't use conditional variance for this one.
Oh.
I had it written down on paper, but I didn't type it up. So.
Okay. Anyway, there we go.
I didn't use the transformation to compute the variance either.
Okay. Oh well. Cool. Does anybody have any questions? I intended you guys just do it straightforwardly from the definition, exactly as Kevin had there. No further questions? Sebastian, it's time to start problem 5.
Okay, I'm sharing my screen now. Can you all see my screen now?
Yes.
So I guess this table was right. The other problems were a mess because I didn't quite get the tables right for the probabilities.
That looks beautiful to me though.
Well, I got three mostly wrong and 4 completely wrong. I think at least I got this one right.
Well, good recalling with the appropriate moment then, I guess.
So I divided the table in 2 bits. Wait, give me a second. So this one for values of the Bernoulli variable equal to 0, and this bit for values of that variable equal to 1. And those are the probabilities for each outcome. And so for the expectation of x, I multiplied this value with wait, no, not that. This value here with its probability here.
Wait a minute, is this for x or for y?
For x.
Okay. So
okay, yeah, it's here. I'm sorry. Yeah, so I guess I was right in the beginning. So, oh no, this looks like a mess now. Well, anyway, so that's how I got the expectation of x, which is like the same as in the other problem with the dice, which is 7.5, 3.5. So the variance of x was obtained roughly, well, not quite roughly the same way. So this is the probability of each outcome. This is the value of x minus the expected value of x squared. And I did that for all the x's for both sides of the table. And
Yeah. So
this
this is exactly correctly set up, I believe. But the algebra went a little funky on you. There should definitely not be any p terms left over in the end. And
yeah, that's what I thought. So when I saw it, but I couldn't get where I was wrong.
let's see if we can see it. You've got 1/6 1 minus p terms, and there should be 1, 2, 3, 4. That says 5 minus p rather than 1 minus p. Where in the second row you've typoed what should be a 1 minus p that reads 5 minus p. And then instead of having the 5, you have the 1 over there. This is a minor dyslexic moment where the 1 goes here and the 5 goes there. And
that wasn't minor. This was a whole mess.
It was, but it's the simplest, like, oops, just wrote it in the wrong place.
Yeah.
That's correct. 1/6, bump, Dumpty, and everything else is it. That's it. That's the only little typo in there.
I think they're, oh, never mind.
Yeah. It's so this is set up beautifully, except for this one typo where we flip the positions of the 1 and the 5.
Yeah, I just kept like I was checking the homework. I just noticed that I made like the dumbest mistakes over and over. I'm like, just
that's okay. Just that's why we're doing them.
There actually is something kind of larger happening here. So for the expectation value and the variance of x, you know what p is. P is 1/6. So I think you're double counting it by having p in your formula.
P is not 1/6. P is the probability he has written out all 12 possibilities. So
oh, but for x, aren't you not considering b the Bernoulli random variable with mean p?
You don't.
Like, I don't know why there is a p. I don't understand, I guess, why there is a p when you're only considering x, which is the dice.
So he has written out all 12 possibilities, and you say, I could have taken 1/6 1 minus p times 1 minus 7/2 squared and added it to 1/6 p 1/6 p 1 minus 7 squared, taken those two terms together, added them together and gotten 1/6 1 minus p plus p, where the p's cancel, and have just gotten 1/6 times the first term, 1/6 times that thing, 1/6 times that thing. That because he has gone over all possible values of b, it's correct. But he could have immediately put together the value 1 minus p, and p added those together and gotten a 1 there, and ended up with 6 terms.
Okay. Yeah, I was just being messy. I guess I'm rusty.
These would have gone away in the first step.
Yeah, this was some lazy math. I'm sorry.
No. This is exactly correct. You've applied the definition. You have 12 possible outcomes. You have the probability of those 12 outcomes, and you summed it all up. You've applied the definition perfectly. That you could have done it much quicker by noticing you have a p and a 1 minus p term repeated over and over again and just smush them together is a useful thing to have seen, because it would have avoided all the chance of a messy complication. But it is not. But is in no sense invalidate your approach.
Yeah, who would think that factoring is useful?
Yeah. Questions?
Should I stop sharing now?
Yeah. All right, Kiana, do you want to try 5B?
Sure. Okay. So yeah, X is a normal six-sided die. B is a Bernoulli random variable with mean P. When B is equal to 0, Y is X minus 1. When B is equal to 1, Y is equal to X plus 1. So for the mean and variance of Y, rather than calculating the values and the probabilities for every single possible outcome, I decided to use this. Can you see my mouse?
Good.
This identity here that relates the expectation value of Y to this conditional expectation, which makes it a little bit simpler to solve. So the way that I got from here to here is that this is very similar to like where you have the expectation value of just X in here is equal to the probability of X being X sub I times X. But instead here, X is this conditional. And so you have the probability of B being B sub I times the expectation value of Y when B is given BI, or when B is BI, summed over all values of I. And so expanding this sum, you have the probability that B is equal to 0 times the expectation value of Y when B is equal to 0. Plus the probability that B is equal to 1 times the expectation value of Y when B is equal to 1. And so since B is a Bernoulli random variable, we know that the probability of B being 0 is 1 minus P. Since it's Bernoulli, we also know that the probability of it being 1 is P. And so what's left to solve is these conditional expectations, which I've done here. And so when B is equal to 0, Y is equal to X minus 1. So this conditional probability just becomes the expectation of X minus 1. Since this is a linear operation, you can separate them. Since 1 is a constant, the expectation value of it is going to be 1. So you end up with the expectation value of X minus 1, which is 3.5 minus 1. Same thing here on the next line. When B is equal to 1, Y is equal to X plus 1. So this conditional expectation becomes the expectation of X plus 1. Once again, you can separate them because it's a linear operator, and the expectation value of a constant is just that constant. And so that's how I was able to derive the two conditional expectations needed to get the expectation value of Y. Plugging those in to this equation here, this is what I got. And so the answer was 2p plus 2.5.
We'll pause there. Are there any questions? That is absolutely perfect.
So
Absolutely.
I'm trying to understand how to do conditional expectations still. And so when you go from the expectation of Y given B equals 0 to equals the expectation of X minus 1, how does that work again?
So if you go back up here to the definition of the problem, you see when B is equal to 0, let Y equals X minus 1. And so that's how you get the conditionals. Down here, this is basically saying, what is the expectation value of Y when B equals 0? Well, when B equals 0, we know that Y is equal to X minus 1. And that's why you can do this.
So we don't really care about Y in that.
No, it basically kind of eliminates Y. You're kind of doing this as a function of B instead of as a function of X, where you would normally do the expectation value of X. This kind of becomes more of a function of B.
Okay.
Like, Yana, I just wanted to say, like, this made it more clear than the way that I did it. I did it like a very messy way. So like, this is fantastic. I just want to like send some positivity out there. This is great. So
thanks. I went to sleep about 3 hours ago.
You can, of course, go from the straight definition, plug in all the probabilities. You'll end up with those 12 terms, and it's and there is a very good likelihood you will have a typo just the way Sebastian did, and at some point it gets swapped. But this is a lot cleaner. Are there, and this is in fact probably the nicest form of the solution, 2p plus 2.5. Anybody, any questions about this half of the problem? And at the end, we'll show the transformation of variable solution too, which is even slicker. So you want to finish with the variance, Kiana?
Sure. The way that I did the variance of y was using this identity. And so I believe this was given to us in class on the lecture slides. That's kind of where I'm getting these from. And so I basically did each of these terms separately. So once again, let me scroll up and just show what the sum looks like when you just have variance of x, because I think that'll make this easier to understand. Right. So when you have just variance of x, this is the part that I'm talking about. It simplifies into this, right? Which is the probability that x is equal to I times x sub I minus the mean, or the expectation value of x, quantity squared. In problem 10, we derive that it turns into this. You can just do the sum over all I of the probability that x is equal to I times x sub I squared minus the mean squared. So you can pull this out of the sum. And so I basically just did this transformation when x is not x, but the expectation value of y when b is equal to b sub I. So going down here, back to where I was, you can see that that's what I did. I have the sum of the probability of b being b sub I times the expectation value of y when b is b sub I squared. And then you pull the mean out and you basically do the expectation value of the expectation value of y given b. I forgot the b equals b sub I there. And so when you go down with this, you have that the probability, this becomes the probability of b being 0 times the expectation value of y when b is 0 squared, plus the probability that b is 1 times the expectation value of y when b is equal to 1 squared. This expectation inside an expectation of a conditional turning into this is exactly how I did part 1. That's just this identity. So I turned this back into just expectation of y since we already solved for it. And then I just plug values in. So the probability of b being 0, it's Bernoulli, that's 1 minus p. I solved for this conditional expectation up here. And so I plug that value in. B is Bernoulli once again. So that probability is just p. This conditional I solved for up here. So I just plug it in. And then we solved for, or I solved for the expectation value of y in the first part of this problem. So I just square it. And so basically when you do all of the algebra, this is what you get for the first term here. And then I just did the same thing for the second term. You have the expectation value of the variance of y given b is the sum of probability when b is equal to b sub I. And this time, instead of x, right, because you don't just have the expectation value of x, you have the variance of y given b is equal to b sub I, because that's essentially like your x here. Then you drop it down. It becomes the same thing that we've already solved for before. Those probabilities and those conditional variances. Actually, never mind. I solved for them down here. So I plugged in those Bernoulli probabilities, and then these variance terms are what you need to solve for. So once again, y when b is equal to 0 is equal to x minus 1. And so this conditional variance just becomes the variance of x minus 1. There's a rule that the variance of a constant is 0. So I think, is that where I'm getting this from?
The variance of a random variable x plus a constant is equal to the variance of the random variable. Adding a constant doesn't change how fat the distribution is. It changes where the distribution is in space, but it doesn't change really the shape of it.
Okay, that's why I eliminated these constants. And so these both just become the variance of x. And so plugging them back into this up here, I have the expectation of the variance of y given b is equal to b sub I is equal to this. And so this 35 over 12 is the second term here. And so I just add both of them together, and this is the variance of y.
That is absolutely perfectly how you do that conditional variance problem. You do it as a conditional variance. Anybody have any questions? This was absolutely perfectly done. So you couldn't be any clearer. If you want to do it as conditional variance, of course you can do it from the straight definitions. You know, where you just end up with a lot of terms in there, and lots of opportunities to typo the algebra. But this, and you'll get 35 over 12 plus 4p 1 minus p. This gives you the best insight into why this answer is 35 over 12 plus 4p minus 1 minus p. The reason is the variance of y looks very much like the average variance of y given b, which is 35 over 12, plus the variance in the mean of y given b, which is 4p 1 minus p. Okay, who did it as a slick transformation of variables and make everybody else look like they're wasting their time?
Should I stop?
Yeah, or unless you did you do it as a transformation of variable too?
I
No.
did not do it two different ways for fun.
Yeah, no. Who's got it as a transformation?
I do.
Okay.
Sure.
Because this one is slick when you transform it.
Okay. So similar to problem number 4, we can rewrite y just in terms of x and b. So basically what we're saying with this first term here is that when b is equal to 0, y is equal to x minus 1. And when b is equal to 1, y is equal to x plus 1. So we can rewrite it like that. And then when we simplify it, we just basically get y is equal to x plus 2b minus 1. So again, like when b is equal to 1, it's x plus 1. When b is equal to 0, it's x minus 1. So that checks out. In terms of deriving the expectation, we can just rewrite expectation of y as the expectation of x plus 2b minus 1. And using linearity of expectation, we just get the mean of x plus 2 times the mean of b minus 1, which is 5/2 plus 2p. And for variance, we can rewrite the variance of y as the variance of x plus 2b minus 1. And assuming, and then of course, since this is a constant, this is just the variance of x plus 2b. And if we are assuming, which I think we are, that x is independent of b, this is just the variance of x plus 2 squared times the variance of b, which is 35/12 or 2.917 plus 4 times p times 1 minus p.
And now you see why there's a 4 in front of that p times 1 minus p term intuitively, because it's a Bernoulli random variable with variance b. You know, that b is a Bernoulli random variable with variance pq, and you put a 2 in front of it, and when you multiply a random variable by something, the variance looks like that value squared. And that is by far the simplest way to do this problem. Questions? Okay. Moving on. Yes. Question? No? Yes. So moving on to 5C with Linnea.
I was really hoping you were going to say like it's a bit of a mess, but
I'm
there
sure.
we go. Oops. Nope. Okay, can you guys see? No?
Yep. Yes, now we can.
Okay, there we are. Okay. Okay, so I'm definitely not slick at all. uh, okay, so basically the covariance has like a ton of terms because you have all these PIJ values. But when I did, because I actually did all of the probabilities out by hand, if you can see that. Can you guys see the page with all the probabilities? It looks like it's frozen.
I only see the covariance X with Y is equal to, I don't, I think there's one, I think you've switched to the next page and I can't see it yet.
Okay, let me try resharing really quick.
Oh, that had it for a second there.
Okay. Yeah, I might have a bit of a slow internet here. Let's try that one more time. Okay, all right. Now we can see. Hopefully. Okay, I actually have a better idea. So I won't be able to write on the screen, but oh my gosh. I think if I just share my actual laptop screen, it'll be a bit faster. Okay, you guys can see that.
Yeah.
Okay, so so for this problem, we have to iterate what are all the probabilities ij. So given x is something, y is also the other thing. What's the probability of that happening? So when I did all the probabilities out by hand earlier,
Yeah.
what you can actually tell, because y is going to be x plus or minus 1, most of the time the probability of having y be like 6 if x is going to be something that's more than 1 below 6, it's going to be 0. So if you can write out this little like, I think it's called a covariance matrix. I don't know if I did it right, but there's kind of a pattern because like I guess I just said, if x is going to be like 2 or something, then there's no way y can be 0 because y can only be 1 or above or below x. So what happens is if you're going to sum over this entire matrix with all these PIJ values, most of them are actually going to be 0, and the only ones that will have a value are going to be on these diagonals here.
Yep.
Where y can take on the values between 0 and 7 because x can go to 1 and y can go 1 below, and x can go to the maximum of 6 and y can go 1 above that because we have both the x plus 1 and x minus 1 abilities, I guess. So what happens is all these terms on the diagonal are going to take on the value given here.
Sure.
If you guys are following that. And then I just went ahead and literally did every single term in this covariance sum here, this guy. And because we already know what the expectation of x and y is, all that changes is just we have to sum over these xi and yi values. So we get x going between 1 and 6. So here going between 1 and 6, and y going between 0 and 7. And yes, so it happens that a lot of those PIs or those P terms are going to become 0, which is why we only have to sum this huge amount of values and not like an even huger amount of values. But yeah, then after that, I just plugged it into the computer and had it do it for me. So
There's only one a little funky somewhere in this.
Okay. I'm not surprised. Yeah.
In this stuff, but here, let me share my version of that algebra if I can. that may have simplified things a little bit. Can you guys see my screen right now?
Yeah.
Yeah. So the first thing to simplify the algebra is I cheated and I used the results from problem 11. And I said the covariance was equal to the expectation of x times y minus the expectation of x times the expectation of y. Since we've already solved for those expectations, this is going to be not very hard. So the first thing I need is the expectation of x times y, which is just x times y, the probability summed over all the possibilities. And there are 12 of them. There's a 1 and a 0, a 2 and a 1, a 3 and a 2, a 4 and a 3, and so forth. A 1 and a 2, a 2 and a 3. This thing has probability 1/6 times 1 minus p, 1/6 times p. I pulled them all out, and I get a 1/6, 1 minus p times that thing, which is a 70, and a pull the 1/6 out, you get a p times this thing, which is 112. Do a little more algebra, and that equals 70 over 6 plus 7p. So I have the covariance is equal to 70 over 6 plus 7p minus the expectation of x, which is 7/2, times the expectation of y, which is 5/2, plus 2p. Multiply these out, all the p's cancel, and you just get 35/12. So it simplifies a little bit, it simplifies a little bit. Does that make sense to everybody? And yes, this is exactly what I think you were doing. Just writing down all the possible values of x and y. You end up with 12 terms, 6 of them with one probability and 6 of them with the other probability. And God forbid I didn't subtract the mean and square, but instead removed it at the end. Questions about that? Does anyone want to show the clever transformation of variable answer? Because that is super slick.
I can share it if no one else did it, but if anyone else did it, they're welcome to share.
I mean, I did it, but I think I guess you can show a screen or I can just write it. It's up to you. Yeah.
I can share my screen.
Yeah, share your screen a little quicker.
Okay. Okay, no. So again, we can just rewrite y as x plus 2b minus 1. So the covariance of x and y can be written as this covariance here. Because 1 is a constant, we can drop that. We just have the covariance of x and x plus 2b, which we can write as the covariance of x and x, which is just the variance of x, plus the covariance of x and 2b, and then we can pull out that 2 there. So we can rewrite that as 2 times the covariance of x and b. Since x and b are independent, this is 0. So we just are left with the variance of x, which is 2.917.
That is it. And that is the intuition for why the covariance between x and y is just equal to the variance in x. Because y can be written as just equal to x plus some other random variable. So the only way in which x and y covary is by sharing an x. So their covariance looks like the variance of x plus a 0 term because we have an independent random variable b. And that is the neatest, easiest, quickest way to get that answer. But you very well can get it by writing down all those 12 terms, squaring, blah, blah, blah. You can get it straight from the definition. Questions? Okay, problem D is mega.
I totally did it wrong, but I'll share anyway. Okay, can we see? So I actually use numbers for the covariance, which I realized was not the move after everyone else just presented. But I just ended up doing covariance over the standard deviation of X and Y, and this is what I got.
Yeah.
But
so,
yeah.
So while so what you wrote the correlation between X and Y is equal to the covariance between X and Y divided by the square root of the variance of X times the square root of the variance in Y. And
yes.
That is correct. Whether or not the individual terms here are quite correct, that's another story entirely. But by definition, the correlation of X and Y is the covariance, which you found here, maybe not exactly correctly, but you found it. And the variance in X you found up here, the variance in Y you found there. If all of those terms had been quite right, you probably would have gotten 35 over 12 over the square root of 35 over 12 times the quantity 35 over 12 plus 4p times 1 minus p. And I'll sort of share that my screen real quick, just so that everybody can have a peek at what the answer maybe should look like. Can you see my screen now? Something
Yep.
up? Yep. So you set that problem up exactly correctly, and when you plug in all the right values, you get something like 35 over 12, repeated lots of times with a 4p 1 minus p term in there. Are there questions? And we will finish for today with Jacoby with a problem, with a statement, a yes or no question. Are X and Y independent? Jacoby around?
I don't think he's here.
Oh well, almost got through the entire, almost everybody made it. Okay, so the last question for the day is are X and Y independent? And one of the facts about independent random variables is their covariance is necessarily 0. So if you calculate the covariance between two random variables and their covariance is not 0, you know for an absolute fact they are not independent. We calculated the covariance here. We got 35 over 12. They are most certainly not independent. And just from the way they're constructed, you can sort of see they're not independent. Y depends on X in a complicated fashion. Does anybody have any questions?
It's not related to this question or this problem, but it is just a general question that I just wanted to revisit to see if anyone else, if we have time to just maybe go over a little bit quickly, because it seems so fundamental, this idea of writing a third variable in terms of the other two variables. And I don't know if anyone else is kind of struggling with that, because I know it's like an old concept and I know it's there, but I think it would be worth it and beneficial to just really kind of deconstruct it, because I think that'll make everything really a lot easier down the road.
Yeah, I was actually.
If I'm the only one that has problems with it, I
was going to ask something similar. Does it? I mean, it looks nice on a homework, but does it get us anything in real life?
Oh.
It's not
no,
computers these days, right?
This is my question, and I've lost connection.
No, you're still here.
Oh, good. Oh, I'm sorry. I just yelled, but my connection is very unstable.
These transformation of variables can be very, very, very useful. we will use them only a few times during the class. But every time we use them, there will have been no other possibility of getting the answer right. You'll be able to immediately write down some complicated sum or integral, and then you'll go, fuck, it's hopeless. And the answer will turn out to be, whenever that happens, if you'd seen a quick transformation, you would have had a way of solving the problem. So it will happen maybe 5 times, 6 times during the course of the class. So it's not going to be like every day or utterly, it's not going to be, the majority of the problems the vast majority of the problems are going to be solvable without having to see anything like these little tricks. But there will be a handful of problems that will be completely impossible without them. And so we introduce these ideas now in these toy problems that you're able to solve lots of ways, with the hope that you will get, that you will think, that you will feel inspired when you can write down an answer from its definition that's unsolvable, and look for a transformation that will make it solvable. And honest to God, Taylor's presentation of her transformations was as logical as you're going to get. But the vast majority of times, at least for me, you just have to see the transformation. You have to just see what you want it to look like and then get it right, if you know what I mean. That
I kind of do, but that's the thing is, like, I think maybe there's just something, basic algebra is fine and I can practice that, and basic statistics is fine and I can practice that. But I think that there are some rules that just have faded from my memory. So I think that's maybe where I'm having trouble seeing it, is I don't remember how to really see it. So like I kind of did a little math on the side for myself where, I showed how S's are related, and I understand that when I plug in a 0, I can cancel things out, or if I plug in 1, I'll cancel some other value out. But it's the idea of getting to the combined related equation that allows me to then plug in values to cancel it out that I just don't see. Maybe it's a matter of me seeing what needs to be set equal to what.
Yeah, I think that's that might be the only good way for you to get the answer. So Taylor had in mind, actually, the way she jumped to it is she has in her toolkit something called an indicator variable, where an indicator variable is a variable that takes on values equal to 0 and 1. And you can think of an indicator variable as like the outcome of a Bernoulli random variable, which is what she did. So she thought of this problem, which was separable as the outcome of Bernoulli random variables, as nothing more than an indicator variable times all those solutions. And that's what allowed her to immediately write down that transformation. She sort of thought about it like an indicator variable, because those are useful concepts in these. They're sort of an indicator versus a Bernoulli is sort of very easy ideas to transform back and forth in your head. But maybe I'm just dumb, but I don't generally see transformations until I see transformations. I can't solve it. Oh wait, if I do this, it will look like something I can solve. And frankly, that's how I did differential equations, as a kid. You can't, for me, I can't do second order differential equations other than to guess the transformation. And I only guess the transformation because I've seen them before. And I don't know a formalized way of knowing when you're going to find a transformation that's going to give you the right solution. I don't see inside. Do you see stuff like that, Sheng-Ji? Do you have like a formalized way of seeing transformations usually?
I guess usually people who've taken statistics would have seen this trick.
Yeah.
It's just a problem of whether or not you've seen enough problems like this.
It's not I don't think there's a lot of insight into it other than you know, you've done it before. You've guessed it before. You've seen other people guess it and you remember. So next time we will pick up exactly where we left off on Thursday, and I will have a new and different ordered randomized list. And if you've learned anything today and want to rewrite some of your solutions for next time, go ahead. And if you don't have to. It doesn't matter. But I think you guys did great, by the way. I think this was really a sort of great class. I'm really very pleased with how you've all done. Any questions before we sign off? Or before I sign off? I guess you guys could start.
For next class, will we be able to bring questions about the second homework?
Absolutely. You can bring questions about second homework right now if you wanted. But, yes, as a general rule, it is not infrequent, it is usual that we will get through most of the homework solutions on Tuesday. And by the time Thursday comes around, we have only a few problems and they go a lot faster than the problems did at the beginning because we're getting better at them. And we often have an hour or more left over on Thursday, at which point students who have prepared might have questions about the next homework. And otherwise, if no one has questions, we'll just wander away. But you're certainly encouraged to look at homework 2 and bring questions Thursday. And we can talk about how to set some of them up, that kind of stuff. And oh, by the way, homework 2 is in many ways very similar to homework 1. The first few problems we did in homework 1 are really Hardy-Weinberg and generalized Hardy-Weinberg. I didn't use any of those words, but I have first tried to explain Hardy-Weinberg in very much a way that abstracted out all the genetics. But when you put the genetics back, you will find it is nothing more than these problems you've already done. And you will find in week 3 that genetic drift is probably kind of sort of the last few problems we did in this homework. But those concepts should become much clearer as we do that homework. All right. Great job, guys. Really, very good job. See you all Thursday.